Okay, 4.6, related rates. Start by looking at a review problem from what we saw the other day. If we have a sphere with radius 10, and the radius changes by a quantity of 0.1 centimeters, which is a fairly small amount in relation to the original radius of 1 centimeter, we want to figure out how much the volume changes. Well, we can figure this out approximately using differentials. So dV equals 4/3 pi r squared times 3, which gives us 4 pi r squared dr. So to find the change dV, that's equal to 4 pi r times 10 times dr. Now dr is this infinitely small amount, and we're giving it a finite quantity of 0.1. So our equality now is an approximation. So the change in volume is approximately 40 pi cubic centimeters. And it's important that we understand that this is not an exact quantity, this is just an approximation. But if we look at a different but kind of similar setup problem, we have that same circle. The radius is changing at an instantaneous rate of 0.1 centimeters per second. So if we have something like a bubble and it's being blown up and the radius is changing at this constant rate, we can try to find how the area or the surface area or the volume changes. So we'll look at the volume. Volume equals 4/3 pi r cubed. R equals 10, and this instantaneous rate of change would be the change of the radius with respect to time. That's dr dt. If we take the derivative of everything with respect to t, we get dv dt equals 4 pi r squared times dr dt. We're using implicit differentiation. Now these are exact amounts, and this is no longer an approximation. To find the rate of change of the volume with respect to time, plug in the radius, plug in dr dt, and we can find out how fast that sphere is growing at that moment in time. And this is an exact answer, whereas the previous example where we're looking at the amount of change, that's an approximation. But here we're looking at the rate of change. This is exact. Okay, we have water draining from a cylindrical tank. Has a radius of 10 centimeters. So since this tank is a cylinder, that radius remains constant. The volume is changing at a rate of 3,000 cubic centimeters per second. We want to know how fast the surface is dropping. So how fast is the height of that water in that tank dropping? So dV dt, that's the rate of change of the volume. It's decreasing, so it's negative 3,000 cubic centimeters per second. R equals 10, that's constant. And we're trying to find the rate of change of the height, so dH dt. Since we have dV dt and dH dt, we need to start with some formula that relates V and H. So the volume of the cylinder is pi r squared h. Now, since r is a constant, we can plug in the constant value right now. Take the derivative with respect to t, and we can plug in our known value of dV dt, and we can find that the rate of change of the surface of the water, dH dt, negative 9.549 centimeters per second. In general, here are the steps we need to take. You might want to draw a picture or a sketch to visualize what's happening in the given scenario. Write down the known information. So if you get a radius or a volume or a rate of change, write that down using our mathematical notation. Write down what you're looking for. So on the last example, we wanted to find dH dt, so make a point of writing that down so you know what it is you're actually trying to find out. Relate all of your variables with an equation. Take the derivative with respect to t, and then evaluate by plugging in all of your knowns and solving for your one unknown. All right, we have a hot air balloon that's rising up. At the moment in time where you have an angle of elevation of pi over 4, the rate of change of that angle of elevation, d theta dt, is 0.14 radians per minute. We want to find out how fast this balloon is going up. So how fast is that height, h, changing? Okay, so we can relate these together with tangent. So that 500 doesn't change. That angle theta changes, the height changes. Take the derivative with respect to t, and plug in all of our knowns, and we can solve for dh dt. Okay, another example here, we have two trucks leaving town at the same time. One truck going east, the other going north. We know how fast they're going. We want to find out how fast the distance between the trucks is changing 6 minutes later. So we have truck A and truck B, and this hypotenuse here represents that distance between them. So we know their rate of change, dy dt and dx dt, and that's in miles per hour. We know that distance equals rate times time, and the time here is 6 minutes, which is 1/10 of an hour. So multiply the rate times 1/10 to find the distance that each truck has gone after 6 minutes. We can find the length of the hypotenuse by using the Pythagorean theorem. 3 squared plus 4 squared equals z squared, and that's a 3, 4, 5 triangle, so z equals 5. And the one thing we're still trying to find is dz dt. How fast is that distance between them changing at that point? So we relate all of our variables, x squared plus y squared equals z squared, take the derivative with respect to t. We can divide everything by 2 to get rid of those, and plug in all of our known information. We know dx dt, we know dy dt, we know x, y, and z. The only thing we don't know is dz dt. And we can solve dz dt is 50 miles per hour.